Well, okay. Good afternoon, everyone. Let's get started. I'm sorry for being quite a bit late. Because of those math stuff, in the desk. But anyway, yeah. We don't have the quiz last week because I was traveling and the classes are canceled. But unfortunately, from this week we're gonna continue with the quizzes. If you can take a look at the announcement, our new quiz will be available today. And but feel free to choose any time between today and the Friday midnight to take the quiz. You got 20 minutes to finish two single choice, multiple choice questions. That should be sufficient. But just don't forget to take it. Otherwise, we won't be able to offer the makeup. Okay, so let us continue with our discussion about the random variables, right? So in our previous lectures, we talked about discrete random variables and continuous random variables, right? So discrete random variables, we have defined probability mass functions, which are kind of like straightforward. It basically just defines what's the probability that your random variable takes different values, right? That's for discrete random variables only. But when we switch to continuous random variables, we mentioned that, say, if we have a continuous random variable, right? So the basic means that your sample space will be continuous, infinite, uncountable, and we're gonna map the outcomes in your continuous sample space to some real number, right? So actually, those type of random variables, this type of random variables are pretty common. For example, the temperature, right? The stock price, uh, height, wife, right? Area, right? They are all kind of continuous, right? So when we are dealing with continuous random variables, we introduce the concepts called probability density functions, right? So PDF. Right? So the definition of the PDF is a little bit not that straightforward in that we cannot say, sorry, we couldn't say that, okay, your PDF at A is just the probability of your random variable takes the value A. Why we cannot define the PDF in this way? Yes, exactly, right? That's the issue. We cannot like just transplant the definition in a discrete case to the continuous case. It's not like directly extrapolate to the continuous domain. The reason is that in the continuous random variables, because your sample space is so intense, right? So dense. If you look at the probability that your value of random variable takes a single value, it will give you simply zero, right? We're not gonna repeat the example, the illustrative examples again. Right? We mentioned that multiple times in our previous discussions, right? Uh, it will end up with zero, right? So that means like our PDF doesn't have any probabilistic meaning. It doesn't mean the probability for a particular event. Instead, we define PDF is more like from a mathematical. Oops. Oh, yeah. Oh, it's dead. Um, yeah, I think I'm too. Sorry, I'm trying to keep a relative far distance, right? So that means we have to use a more mathematical definition. What does it mean? Like it means that I'm gonna propose such a function, right? So that if I want to compute the probability, the random variable falls in any range, right? Say A and B. This probability, remember, this represents a particular type of events, right? The random variable's value falls in a range, right? If this probability can be expressed as an integral from this range, the integration function is some function, right? Some non-negative function. And this non-negative function, of course, is non-negative, and their overall integral in the real space is 1. Then we call such an integral function as the PDF, right? So you see, it's a little bit indirect, but I can feel like, okay, I want to have some kind of underlying accumulator, right? From that, I'm gonna accumulate my probabilities throughout a range. Then I can give my whole probability for that range. So this gives the definition of the PDF. Does it make sense? Right? So if you still feel uncomfortable about this definition, that's totally understandable. I was confused about this concept when I was an undergrad student as well. You just memorize that. That's the way. That's the mathematicians who developed this, who invented this concept. Okay, so that's the PDF, right? Then we also have this CDF function, the cumulative distribution function. So this one is kind of like totally or exactly the same as the definition in a discrete random variable case. Basically, for CDF function, it is just the probability that your random variable takes value less than or equal to A. That's it. Right? That's the PDF. That's the CDF function. And if you write it in terms of this, the PDF function, it's just an integral from minus infinity to A, right? The upper bound, upper limit is A. And you integrate with our PDF function, right? From minus infinity to A. Okay. And from this definition, we can immediately get to the conclusion. That is, if I can take the derivative of the CDF function, that is, I'm gonna take this, take the derivative of this integration, right? With respect to the upper limit of the integration, right? It will immediately give the PDF function evaluated at A. Any questions so far? Yeah, overrun is it's some kind of like how our mind like refresh, and then we get to our definition, right? So you can see almost all the continuous random variables are characterized by PDF and CDF functions. Of course, in the probability theory, there are additional functions which are of interest, but not all our scope, like moment generating functions, characteristics functions. But those are not our focus, right? All we need to know is that, okay, we need to, when we model something, right, as a continuous random variable, then we need to talk about what is the PDF, what is the CDF. Okay. And then we talk about different continuous random variables, like Gaussian random variables, exponential random variables, Pareto distribution random variables, right? So each random variable, they are specified by a particular PDF, and we have given the form, and we have given the CDF function, if we could recall, right? And the simplest one could be the uniform random variable distribution, right? if you could remember, this is just saying, okay, my PDF is just a constant, right? So 1 over beta minus alpha, something like this, right? So if you don't remember, that's totally fine. Just to look at our previous slides. Okay, that's what we have discussed so far. So now we want to extract important properties about random variable from its probability density functions. You see that there are two most important property of a random variable. One is called the expectation. The other is called the variance. So our task is to figure out the definition and how to compute the expectation and the variance for a random variable. Okay, so first, what is expectation? So expectation in some literature, it is also called mean. Right? It's the same. Right? They're interchangeable. So intuitively, expectation means on average, what does a random variable take? Right? So we know that the random variable can take many different values, right? So we would like to say, okay, on average, what's the value those random variables will take? Like say, the random variable can have a 0.9 chance to take value 1, right? And have 0.1 chance to take value 0, right? So on average, this value, the random variable can take some value in between 0 and 1, right? But of course, this in between will be more biased toward 1, right? Because why? Because it has a larger chance, much larger chance to take the value 1. Right? So expectation is just a way to reflect what is the average behavior of a random variable in taking their values. Okay, so for discrete random variable, the definition of the expectation is straightforward. It's just a weighted average of every value that random variable can take. And the weight is just the corresponding probability the random variable takes that value. Right? Say your random variable x, which is discrete, right, can take a set of values like a1, a2, and a3, right? So now, if I want to compute the expectation of x, I'm gonna do a weighted average of a1, a2, a3. And the weight is the probability of the random variable takes that value. Right? If I write it explicitly, it will be, say, a1 times the weight, right? The weight is the probability of the random variable takes that value, plus a2, the probability x takes a2, plus a3, the probability x takes a3. And that's it. So in general, like you have say m discrete values x can take, then your expectation is just the weighted average of all these m discrete values weighted by the probability x takes each of those values. Any question? Okay, so you can understand the concept of expectation in another way. Like you can imagine if you're allowed to do the same experiment many times, right? And in the first time, you might observe the value. The second time, you might observe another value. In third time, you observe a third value, right? You can imagine like you take this, you repeat this experiment many, many times, and you take the average of all the observed values of the random variable. That's what the expectation would like to reflect. Okay. So now let us look at some example. Right? We start with the one of most common used discrete random variable, which is called Bernoulli random variable. Okay. So Bernoulli random variable is talking about if you do a experiment with binary outcomes, right? What's the chance you succeed? What's the chance you fail, right? Like you flip a coin, what's the chance you see a head? What's the chance you see a tail, right? So, so here P parameterize this Bernoulli distribution and gives us the probability you see success, right? So basically, we say a random variable X follows a Bernoulli distribution parameters by P. It means that the probability X equals to 1 is P, right? And the probability X equals to 0 is 1 minus P, right? And X, can X take 3? No, why? Yeah, it's a Bernoulli random variable, right? You're only allowed to do one trial, your outcome is either 1 or 0, right? Your outcome is binary. It cannot be, there won't be a third outcome, right? So now, let us see how we're gonna compute the expectation. Right? As we know that X can take the value, that is the range of X is 0 and 1, right? So we take the expectation as we defined, we're gonna compute a weighted average of those two values that X can take, right? So the weight is the probability the random variable takes that value, right? So it has two possible values, 0 and 1. So we multiply 0 with this weight. This weight is probability X takes 0, right? 1 minus P, right? So, and also another value is 1, and the weight is a probability X takes 1, right? Which is P. So now you do this weighted summation, you get the expectation of X is P, right? Any question? Yes. Yeah, that's a very, very, very well-known result. So basically, if you know, okay, I have a Bernoulli random variable with P, then the expectation must be P. There's some kind of like some kind of a conclusion should be planted in your mind. You should reflect this spontaneously, right? No need to in for why. Right? Just you know that okay, this is a Bernoulli random variable. Then the expectation will be the probability the variable takes 1. Okay, another question. Okay, great. So now let us consider a more complex case, right? So we consider a geometric distribution random variable, right? So what is a geometric random variable? What is the geometric distribution about? Exactly, right? So the geometric distribution talks about, suppose you do multiple independent Bernoulli experiments. But I would like to say, okay, after how many after a certain number of trials, when can I get the first success? So if X follows a geometric distribution, then X equals K means the first success appears after the kth trial. It implies that, okay, the first K minus 1 trials will be a failure, right? And then case trial succeeded, right? So that means your range of the random variables will be just positive integers, right? Its first success might be in the first trial, second trial, third trial, right? It could be as large as possible, right? So, and the probability X takes any positive integer value K is what? How do we calculate its probability? Any thought? How do we compute the probability that your first success is after kth trial? The critical thing is that we can't miss the first K minus 1 failures, right? So could anyone tell me what's the what's the formula to compute this probability? I wouldn't say plus, right? Because if I say, okay, X takes the value K, means that, okay, the first K minus 1 trials all failed, right? And until the case trial succeeded. And then what's the probability? Yes, exactly, right. So remember, we're doing multiple trials, right? Each trials are independent to each other. So you succeed with probability P, you failed with probability 1 minus P, right? Your first K minus trials all failed. That means the probability is 1 minus P to the power of K minus 1, right? And then the case trial succeed, right? The probability is P, right? So you multiply them all together, you get the probability you got your first success after case trial. Does it make sense? Is everyone comfortable? Right. I mean, we discussed about this in detail when we talk about binomial distribution, right? Like multiple Bernoulli trials, and then we reduce it to like geometric distribution. If you feel like question, this one, yeah, this is something I'm gonna discuss right now. Yeah, okay. But first, we need to figure out what's the probability mass function for geometric distribution, right? Is everyone comfortable about this? I mean, the probability, how do we compute how do we compute the probability X takes different values K? Okay, so now, given this probability mass function, right, we can compute the expectation. Now we follow definition, right? So the expectation is the weighted average of all the values X can take. And the weight is actually the probability X takes that value, right? How many values could X take? How many? Infinite, right? It's not real numbers, but it's still all possible positive numbers, right? All possible positive integers, right? And there are infinite many positive integer numbers, right? So that means your expectation will be a summation from 1, the minimum value you can take, to infinity. Okay? And for every possible value, you need to weight it by the probability the random variable x can take that value. Right? That's the definition of the expectation. Does it make sense? Okay, so now we know the probability x takes k is this guy, right? We just do some substitution. We have the summation k times this probability is this guy, right? Just p times 1 minus p, k minus 1. Okay. So as long as we can compute this series, we are able to calculate, we're able to get our expectation, right? And unfortunately, this calculation is not straightforward. Right? So first, it's not geometric sequence, right? And you don't want to like leverage some kind of formula, like the successive terms, their ratio won't change. The ratio actually is changing. You see that, right? Because there's a k, right? There's a k as a factor for each term, right? So you cannot directly apply the formula for geometric sequence, right? And also, it's not like the difference between successive items are constant. They are definitely not constant, right? So the calculation of this requires a little bit trick. I would like to review this, and so that we can all practice our calculus 1 a little bit more. That will be beneficial for this course. Okay. Okay. So the question is, how do we compute this summation, right? So obviously, if you just look at the terms, each summation, right, you won't see any patterns or formula that can directly applicable. But if we can make additional observation, right? So we see that there's a common factor for every summation, right? Which is p. We can just move it out of the summation. Right? So let's move p outside, right? So in the summation, we need to add all k times 1 minus p to k minus 1, right? So what does this look like? Let's associate with the derivative rules, right? So when we calculate the derivative of a power function, right? If we take this guy, take derivative of this guy, what's that? I mean, x is the variable, right? A is a constant. X to the power a. If you take derivative, what's that? Yes, exactly, right? We need to recite it, right? We need to recite every day to make sure we never forget all these rules, right? So a times x a to a minus 1, right? So if you look at this, what can we observe? So here you can just view p as x, right? So this essentially is to apply the derivative over 1 minus p to the power of k, right? Of course, the derivative is applied to p, right? To p. But if you want to apply to p, you have to take a minus sign in front of it. Why is that case? We can just verify it with chain rule, right? If you just take the derivative over P, according to chain rule, you're gonna first view this guy as a whole, right? So it will be K times 1 minus P to K minus 1, right? And then you take the derivative of 1 minus P with respect to P, right? Which is minus 1. Okay. Right? So that means if you put a minus 1 in front of it, if you take minus 1 in front of it, right? So now 2 negative becomes positive. You recover this guy, right? Does it make sense? Right? So basically, we now observe that each summand essentially is to take minus of 1 minus P to the power of K, take the derivative with respect to P. Again, if you feel uncomfortable, you just need to verify by yourself. There's nothing, it's just our chain rule with the rule of the derivative over power function, right? And what's the usage of this? Let us try to first we can move this minus sign in front of the summation as well, right? So it will be minus P times summation K from 1 to infinity, and inside summation, each summand is 1 minus P to the power of K, and then take derivative. Does it make sense? Everyone's comfortable? Okay, so now consider the rules when we do derivatives. Say I got a function, right? Fx, 4x, 2x, 3x, right? This is summation of 3 functions. So I take the derivative over the summation is equal to what? It's the sum of derivatives, right? So I can do the derivative of each function and then sum up, right? So similar things can be applied here, right? So we want to compute the summation of the derivatives. It is equivalent to computing first the summation and then take the derivative over the whole summation. It's the same, right? So with this guy, if we first compute every derivative and add them together, it's the same as like we first add all those functions together and then take the derivative over the whole summation. Right? Let's try to apply this, right? Does it make sense? Right? So let's try to apply this. That means I can first do a summation from 1 to infinity, 1 minus P to the power K. I add all them together, right? And then I do the derivative with respect to P. Does it make sense? So what's the benefit of doing this? What's the benefit of I just adding all this 1 minus P to K together and then do the summation? If you look at the summation, what can we observe? Now this is a summation. Yeah. Yes. Yes. Now if you look at the summation, you see the successive items, they have the constant ratio, right? So this is a geometric sequence, right? That means we can apply the formula, right? For a geometric sequence, it's like a0 times r, a0 times r squared, right? So you see all the successive terms, they have a constant ratio. So this is a typical geometric sequence. So that means we can apply the, oh, sorry. We can apply the formula to compute the geometric sequence, which is the first term. The first term is 1 minus p, right? And 1 minus the ratio to the number of terms. Here we have infinite number of terms, right? And then divided by 1 minus the ratio, which is 1 minus p. If you kind of forget what is the summation formula for a geometric sequence, yeah, I just write it like, if you have a geometric sequence like a0, a0r, a0r squared, see a0r m, right? So the summation is a0, the first term, times 1 minus r to the power of the number of items in the sequence, right? So here is m plus 1, right? And divided by 1 minus ratio r. Okay, that's the formula. If you apply the formula here, it will give you this. And the good thing is that because 1 minus p is less than 1, right? And you have an infinite number of terms. So that means the number of terms infinite, and you take 1 minus p to the power of infinity. Infinity, what's the value? 0, right? If you take a limit of multiply some number between 0 and 1 for infinite amount of times, what's the value? Will be 0, right? So that means this result is simply 1 minus p over p. Right? I mean, if you don't say that, it's fine. I mean, I highly recommend everyone to follow this, to replicate this derivation after class. We just want to review the k derivation is 1 minus p minus 1, right? So now you have the whole summation here. You just need to take the derivative over p, right? What's this derivative with respect to p? Can anyone just read it for me? Yes, it's a minus 1 over p squared, right? And now we see the outside there's a constant factor minus p, right? You multiply them together, you end up with this 1 over p. Does it make sense? Okay, I mean, this expectation calculation is not that straightforward, but it's really a good way to help us to recall what we have learned during calculus 1 or 2. Okay, let's take 5 minutes rest and then continue. Yes.
So can we treat the fact that it will fail because it's numbers, the number of attempts till success, right?
Yes.
Can we treat that the toaster fails on the 8th or at least
No.
7th?
The toast will keep filled until the 7th, right?
Yeah.
Yeah.
Yeah, like at least 7 tries. So can we treat that 7th or above try as like the success in the geometric distribution definition?
What do you see that? Can repeat again?
I said, can we treat the fact that the toaster will fail on the 7th because the geometrics defined as number of tries till success, right?
Yeah,
can we treat
this is a little bit beyond that.
it is?
Yeah. So you need to think about that. This is not just apply the geometric distribution. So remember, so at least the 7 pieces, right? So that means it might break.
Is it like over the CDO?
Yeah, it could be 7, 8, 9.
7 till infinity, and you
yeah,
can
yeah.
integrate from 7 to infinity.
Yeah, but you can consider like there are too many, but you can consider another way, like probably it will fill at 1 piece, right? 2 piece, 3 piece until 6 piece, right?
Well, since we're considering at least 7 pieces and up, can I take the PDF and integrate it from 7 to?
You can do that. I mean, that's not no way, but might not be an easy way to do that. You can do that. It's doable. Another way is that you consider other than this event, right? And in what other cases the toaster will fit
from 0 until 7.
Yes.
That
and then then you can subtract the 1 minus that one.
1 minus
the integration from 0 to.
So it'd be 0 to 7 of our geometric distribution of 1 minus p to the k inside.
Yeah.
K was 7 minus 1 is probably just like that and then dx.
Yeah, I wouldn't say it's an integration because this is this will run there. We should consider summation.
Okay.
Yeah, we should consider other than what's the complementary events for this, right? That means like okay, we're gonna have the toaster fill with 1 piece, right? 2 pieces, 3 pieces, until 6 pieces, right? And we just add the probability of all those events together and then subtract 1 by them without the probability of that you have at least the same pieces, right?
If it to consider it discrete, would we just consider it until 7? Because if we consider, because this is continuous, if we're just considering like putting pieces in until the toaster fails, because that's like 1 or 0 to infinity, right?
Yes.
Okay.
Yeah.
Thanks.
So trying to solve this one, I had to talk to somebody else to get the right answer, I think. I originally thought that you'd have to take a derivative from this range. I don't know if I was making up in calculus, like I did derivative of, since it lies within this section, I did derivative of 2x cubed minus x squared from.
For this one, what's this? What's this big F represent?
It represents
the cumulative distribution, right?
Yeah, I don't know what that exactly means.
So the definition, what's the definition of cumulative distribution?
It gives you like a range of values like based on inputs.
Yeah. But has some probability meaning, right? So the probability x, the meaning of the probability x less than or equal to something like so x, for example, if you put the small x to be 2, then the value of f2 is just the probability of the random variable x takes the value less than or equal to 2.
Okay.
Right?
So it already establishes a range. You have to take an integral or derivative.
I mean, you can use the derivative to get the PDF and then do the integration. That's one way, right? If you want to do that, that's okay.
Well, why don't you have to do that? Why can't you just plug it straight in?
Yeah, that's my point. Yeah, that's my point. Yeah, yeah. I mean, it's up to you.
Yeah.
You can use whichever way you want to calculate.
Okay, so what's the difference between, like, what does a PDF show when compared to a CDF? Because for a PDF, you can,
PDF basically is a derivative of CDF.
yes.
Yeah.
Okay. I get that relationship.
Yeah.
When it's asking for which type of variable, is that asking like discrete variables? Is that what that means?
Yeah, but it's not sufficient.
Okay.
Yeah. If you just just discrete, you won't get full point, right? You should better to indicate which distribution follows, right?
Oh, okay. That's
Yeah, it could be
that's-
binomial, could be
like
it could be
geometric.
geometric, right?
Yeah. Okay. That's what I was curious about.
Yeah.
If that and
Okay. Okay. So let's continue. So now we do let's do a simple in-class exercise. Right? So let us consider we roll a six-sided die, right? And you got equal chance to see every side, right? So that means you have a. So if you look at the side, right? I mean the side upside, right? So it can take six possible values. So 1, 2, 3, 4, 5, 6. Right? So because this is kind of like an equal chance die, that means the probability you see any point in the upside is the same. It is 1 over 6. Right? And then if we want to calculate the expectation, as we mentioned, we just do a weighted average of every possible value x and take. So you got 1, 2, 3, 4, 5, 6, 6 possible values, right? Each possible value has an equal chance. That means their weight is 1 over 6. So the expectation is simply average of this 6 value, which is 3.5. Any question? Okay. So those are about the discrete random variables. Now let us talk about continuous random variables. So for the continuous random variable, we know that it's not meaningful to talk about what's the probability the random variable x takes a particular value, because that probability will simply be reduced to 0, right? So then when we calculate the expectation, we need to seek for the help of the PDF. So basically, we do an integration from -infinity to infinity, and we integrate x, the value, the range, in the range of the value, in the value range of x with the PDF. And that's it. So you can imagine this is kind of like a continuous generalization of the summation, right? So the discrete case, we know that, okay, we look at every value x can take which is denoted as AI times the PMF of PMF at AI, right? And now in a continuous random variable, we have a continuous PDF function, right? And now the summation is extended to integration. And you integrate across the whole value range of X. And you integrate X in this range with the probability density function F in this range. That's the definition. By the way, what's the integration of f of x alone? Yeah, it's just one, right? Remember, this is the definition of the PDF. Okay. Any questions regarding the definition of the expectation? Great. So now we just apply this definition and look at a few examples, right, to strengthen our understanding. So the first one we want to look at is the exponential distribution. So as we mentioned, the exponential distribution, the random variables value range is the positive numbers, right? So as we mentioned, it's just usually you use to model, say, the life for a light bulb, or the inter-arrival time between the buses, or the server of service waiting time, and so on, right? So the PDF, the probability density function of a exponential random variable is lambda times e to the power of minus lambda x. And here lambda is this parameter which is bigger than 0, right? So this is just the fact, right? Don't need to ask why, right? We don't need to ask why. And then we want to calculate the expectation according to the definition. This will be the integration of the random variables value with the PDF in the range, in the value range, right? The value range here is 0, between 0 and infinity. Right? So substitute the form of the exponential distribution density PDF. You have this, right? And then next thing is just to calculate this one. How do we calculate this? Any thought? Yeah, this is again, this is the practice of our calculus 1. Yeah, let's do it together. Right? So we're gonna use the trick here. We're gonna use is called integration by parts. Right? So if integration by parts just means like if you got an integral over something like this, x dy, we can write it as x times y and evaluated from this b and a and subtracted by a and b. You just swap x and y. Right? That's the integration by part. I mean, if you feel this is kind of like a blurred, it's not very clear, it's just open the book, right? Open some book you used or you hated a long time ago, right? But anyway, we have to practice this. So for this guy, and for this integration, we're going to leverage the fact that this guy actually is derivative of minus e to the minus lambda x. Does it make sense? Right? Yeah, we can verify this, right? If you take the derivative of this guy in the parentheses with respect to x, just memorize the rule, right? So this should be minus, and take exponential, take derivative of exponential of anything is exponential of itself, right? It's e to the minus lambda x, and then you take derivative for this part, which is minus lambda, right? And then you end up with lambda times e to minus lambda x, right? Which is here, right? Yeah, it's just the practice. There's nothing nothing special. Okay. So now we can write this integral as 0 infinity x times d minus e to the minus lambda x. This guy, right? Look at the formula here. Right, we just apply that. Just apply that. So this guy actually is y, right? So we're gonna do the xy and evaluate at b and a and do the subtraction, right? So it's x times e minus e to the power of minus lambda x and minus so the upper bound is upper limit is infinity and lower limit is 0, and subtracted by we're gonna swap x and y, right? So y here is minus e to minus lambda x and dx, right? Does it make sense? And you got 2 minus, so they're canceled. So you can just remove this guy. So let us look at this guy. This guy is x. I want to write it more clearly. Okay. So what is this guy? Y is 0. The answer is right. It is 0. Right? So why do we how do we see this, right? So this guy equals to what? So we're gonna evaluate x times e to the minus lambda x, where x equals to infinity, subtracted by x times e minus e to minus lambda x, where x equals to 0, right? So that's the definition. So this latter term is simply 0. No one disagrees, right? So the case of how about the first term, right? Yes, yes, yes. I will put it more in detail, right? Put it point more in detail. So this guy, if you look at the first term here, right? So this guy actually is minus x to the power of e to the power of lambda x, right? And then x takes infinity. That just means like you're gonna take x, the limit x to the infinity, right? So this one is 0. Why is this 0? Because imagine you in the numerator you grow x linearly, right? But in the denominator you grow x exponentially, right? Of course, the denominator will grow like much faster than the numerator. Then at limit, this ratio must be 0. Does it make sense? That's simply because the denominator, the exponential growth is way faster than the linear growth. So their ratio will become smaller, and limit will be 0. Right? If you want a more rigorous proof, just find our textbook is is a well-known result. Right? You can use whatever. You can use like classical way to prove that. I mean, the definition of limit, delta sigma language, right? If you still remember what's that, right? Or you can use rho beta rules to do that. Both will give you the same result, which is 0. But anyway, we know that, okay, the first term here is simply 0, right? So the only thing remaining is the second term, which is 0 minus infinity e to the power lambda x dx. If you do this integration, it will give you 1 over lambda. Okay, this is how we get the expectation of exponential random variable. Right? We recommend everyone to replicate this derivation to recover this result by itself, because it's really good practice of calculus. Right? Any questions so far? Okay, great. So the second example is the Gaussian distribution or normal distribution. So we mentioned the normal distribution, right? So a normal distribution is parameterized by two parameters, mu and sigma square, right? So here for convenience, I'm gonna just write down the PDF for Gaussian distribution, which is 1 over square root 2 pi times sigma, and it is exponential to the power of 1 over 2 sigma square x minus mu square, right? So you see that the PDF itself is determined by two quantities. One is mu, one is sigma square, right? And the natural question comes, what's the expectation of this distribution? According to the definition, it will be, you have to do the integration, right? Integration of the x multiplying with fx with dx, right? So fx is this hateful term, right? It's 1 over this square root 2 pi and the sigma and the e to the power of this guy, right? And this one, I mean, if you don't feel, if you have some time, you can try with that. It is doable. I mean, you can definitely write down the antiderivative function and calculate that. And perhaps you need to use several integration by parts. I'm not gonna spend 20 minutes doing that. I will leave it as an exercise for you. It's really, really good practice of your calculus. But here, just to give you the result, this guy is simply mu. Again, this is a very well-known results. Right? And that's why when people are talking about a Gaussian distribution or a normal distribution, we say, okay, what is the expectation parameter? Because once you specify the mu, the PDF itself will lead you the expectation being exactly mu. Okay, any question regarding this? Okay. So a very, very important property about expectation is called linearity. What does it mean? It means that, okay, if you do some kind of linear combination of a set of random variables and then take the expectation, you can first calculate the expectation of each random variable, then do a linear combination. So here, we can look at this one, right? So if we do a linear combination of x and y, where x and y are two random variables, they might respect a total different PDF, right? And then if I take expectation on their combination, it is the same as I first do the expectation on x and on y, then do a linear combination. Okay. So the proof of this is really simple. But here we want to we don't want to talk about right now because that will use the concept called marginalized density function and distribution. Right? So we'll talk about that later. Right? But here we just use it as a fact. And another thing I want to mention is that if you take an expectation of a constant, so A is a constant, it's not a random variable. What's that? It's simply A. It's just a constant. Right? So this is correct in both, I mean, if you prove that, of course, you need to prove that, and you can treat constant as a very special discrete random variable. It can only takes one value, right? And the probability of you take that value is 1, so your calculate expectation is just 1 times A, which is A, right? Or intuitively, you can imagine, okay, if you got a random variable, it always takes the value A, right? On average, it will take the value A for sure. Does it make sense? Okay, let me repeat, right? So if A is a constant, right? So you can imagine, okay, I got my random variable A. It only takes a constant value. So no matter how you repeat the experiments, you observe the value of A is always A, right? It's always a fixed value. Then on average, the value won't change, right? On average, it's still A, right? That's why the expectation of constant will also be a constant. Right? And if you want to prove it in a more rigorous way, like, okay, that means, okay, I have a random variable X, right? And the value range of X is just a single value A, right? And that means the probability of X takes A is 1, right? Now you want to take the expectation of X, it's just 1 times A, which is A, right? That's another way to show that the expectation of constant is just a constant. Okay, any questions so far? We got the facts, right? The linearity of the expectation, right? And the linear combination of random variables, then take expectation is first to take expectation of each individual random variable and then take linear combination. So next, we're gonna use this rule to very efficiently and smartly compute some expectation. So let's see. We roll dice, right? We roll 10 dice. And we see the 10 points, right? So now, so let's denote the points for each dice is x1 to x10, right? So now I want to look at the summation of all those 10 points. So which I denoted as y, right? Y actually is a summation from x1, x2 to x10. Now, if I want to compute the expectation of y, how to do that? One way of doing this is that, okay, now I want to consider what is the PDF for y, right? So you have to derive some PDF function based upon like 10 dice rolls, right? For PDF, for every rolling, right? For each x1, x2 to x10, you know the PDF, and but their summation, if you want to compute the PDF for their summation, it's not a very straightforward thing. But if we look at, if we utilize the linearity of the expectation, right? We know that y is simply the summation from x1 to x10, right? So we know the expectation of the summation is the summation of expectation, right? This is what this linearity of expectation says. So that means I can do the expectation of each individual dice roll and then add them together. Right? And we have in our previous discussion, we know that the expectation for one dice roll is just 3.5, right? We know that's equal chance, 1/6, and one, you got all 6 points, right? Add them together, which give you 3.5, right? So now, for each dice rolling, the expected or expectation of the points is 3.5, right? You just add 10 such expectations. That means you multiply the same expectation for time. So that's why you multiply them by 10, which gives you 35. Does it make sense? Any question? Okay. This is a very, very useful property, especially like we'll know, okay, the relationship between the random variables, if they're just a additive relationship, meaning some kind of linear combination or weighted combination, then you can always leverage this property to compute the expectation, rather than looking into, okay, what's the PDF of this newly generated random variable, right? A linear combination of those, a bunch of other variables. Another well-known example is this binomial distribution. So remember, the binomial distribution is to repeat the same Bernoulli experiments for n times. And we want to look into what's the total number of the successes. If you use, like for example, you flip the coin, right? If you flip the coin for 100 times, I would like to say how many times in total I can see heads up, right? That's what the binomial random variable describes. So now if we want to compute the expectation of x, of course, we know that the PMF of x, right? X equals to anything like I equals to k, is you have to first compute a combinatorial number, right? Choose k out of n and times p to the power of k, 1 minus p to the power of n minus k, right? And then you just add up all possible values, possible k that x can take, multiply with the probability, right? Doing that is doable, but not very fun. Right? Instead, there's another way, right? So if you look at x, right, you know x, the total number of the successes can be written as the outcomes of every Bernoulli variables, right? So every Bernoulli 12, you will see an outcome, which is either 1 or 0. 1 represents success. 0 represents failure, right? If you add up all x1 throughout to xn, right? Their summation actually is the total number of the successes, right? Because all the failures are zeros. And then if you want to compute the expectation of their summation, you can first calculate the expectation of every single Bernoulli random variable, and then add them together. Right? So every single Bernoulli variable, their expectation is p, right? We have derived that a moment ago, right? We add them together, n such Bernoulli random variables, so the expectation is np. So this is exactly the same as you use the standard definition to compute the expectation of x. Okay, let's stop here today and see you on Thursday.